It says on my whiteboard there that torque quantifies how effective a force is for rotation. So we're defining torque in this topic. And if you looked up the definition, maybe online or in a more mathematical or mathematically oriented physics text, maybe slightly advanced physics text, this is the formal definition of torque, but I've labeled it as kind of advanced, but I'm just putting it there because you definitely, if you do an internet search, you might run into that thing. Maybe a more basic definition that captures the idea behind this formula is that torque is equal to moment arm times force. And that's actually kind of what this looks like, because R is moment arm and F is force. It's just here there's vectors. This looks like the time symbol, but it turns out this is the vector product for vector mathematics, and that has a somewhat more complicated definition than I'd like to go into for this class. And although you may have experience with that, if you don't, it's okay. I'm not expecting it for this class, so it's either way. If you want to use it, actually, I'm going to probably discourage that for this class because it's pretty complicated, and in some senses it's great to do everything as complicated as possible. Actually, I'm kidding. It's not really, right, to make everything as complicated as possible. But in that sense, it's like in physics, why do we not always do every single thing based on the rigid definitions that are stated in math text? It's like, well, it makes things too complicated. And sometimes it's simpler to just draw a picture and use the concepts we want from those math definitions and that we understand to arrive at results. And the concept behind torque is we're talking about force that is trying to rotate a system. So it's kind of like if you're trying to turn something with a wrench. Maybe it's a nut or a bolt or something that you're trying to turn with this wrench here, right? And I've drawn sort of three scenarios here. And so a simpler formula that governs these three scenarios perfectly is tau is equal to RF sine theta. That gives you the magnitude of the torque. It turns out this more advanced formula would, if you used all the mathematics that it entails, would give you both the magnitude and the direction of the resultant torque. There's a theorem that says that the magnitude, though, that comes from this is exactly equal to this RF sine theta. So that's what makes that safe. So we're going to usually use that. That's going to be kind of our go-to definition. But the way that works is like if I'm trying to turn this wrench, right, this left picture here I think represents the most effective way to turn that wrench. If I apply the force at right angles to the handle, that's going to be an effective way of trying to turn a bolt or something like that, right? That means it's at right angles to the moment arm vector. So R is the moment arm vector. It's not necessarily a radius, but maybe one way of thinking about it is to say it represents the radial distance from the axis of rotation to the point of application of the force. So in that sense, it being a radial distance, maybe there is kind of a radius in there, or radial, right? That's why it's R. But again, it is really the moment arm. So thinking about all that, and definitely if you have a situation where there's a radius or you assume it's going to be a radius, you want to be careful because it may be something different, right? Maybe not presented to you in that exact way. Anyways, this next picture here, the middle picture, kind of is intermediate, right? Like this force would have intermediate efficacy for turning a bolt because it's not exactly at right angles, but it's not like this one over here to the right where it's totally horizontal. I've just said, hey, what if it's at 45 degrees? Or maybe is it at 135 degrees? Or maybe, well, I guess given the way it's pointing, it's maybe in the third quadrant. What would that one be, right? Is that like, let's see, 225 degrees, I think, something like that. But I'm thinking about the angle between R and F, and 225 is definitely not going to work for that because that's what this angle is meant to describe. But depending on how you draw the R vector and the F vector, you could get an angle between them of 45 degrees or 135 degrees. Maybe the formal mathematical way, I think, to do it is to put both of the vectors so that their tails are kind of coming from the same point. And if you did that here, then I think this one would be 135 degrees. But if you just said, hey, let me just take the smallest angle between those two vectors, and it turns out both options work. And so in that sense, it's good to know there are some options there. The reason why is the sine of 45 and the sine of 135 is going to be the same. There is some perhaps esoteric identity that you could maybe look up in some huge table of trig identities that says that if you take the sine of an angle or if you take the sine of the supplement of that angle, in other words 180 minus that angle, you get the same result. And that's kind of how this works here, but you don't need to remember all that. Just know that it doesn't matter. As long as it's an angle between these two, it'll work whichever one you go with, right? So in that sense, this force, if it's applied perfectly horizontal here, maybe it's actually 180 degrees because it's pointing to the left, whereas moment arm vector is pointing to the right. But if you just said, hey, that's 0, that's fine too. But getting back to effectiveness of rotation, I think we can all agree that this last picture right here is not going to be at all effective for rotating a bolt. And we're going to analyze in the next chapter in a little more detail, like how do you relate torque to how effectively something rotates? And in particular, we're going to be able to relate that to angular acceleration, which is maybe not what we're trying to achieve when we're rotating a bolt. This is more of a quasi-static kind of situation. You're probably not trying to get it like spinning, right? Because there's like probably friction and stuff and going on with the bolt and whatever threads it's connect to or something. But anyways, so this, again, more quasi-static. And so for statics, we're going to see in a later topic that in addition to forces balancing, as we've looked at, another condition for an object remaining static is that the torques will have to balance, because if they don't, the object might rotate out of equilibrium. So that's part of the reason why we're doing all this. Now let me get to the last two parts here of the key concept slide. It says there right-hand rule. So what does that have to do with? So this kind of advanced definition includes the direction of torque as well as the magnitude. And I said RF sine theta will take care of the magnitude for us, but what about the direction of torque, right? How do you establish a direction of rotation? Well, it turns out there's a right-hand rule for that, although it's a little bit weird because if I looked at like this wrench here and I said, well, which way is it going to move, right? You might say down, right? But does it really just move down, or does it like, well, one end kind of goes down, right? And it would kind of, right, rotate in a circle kind of fashion, so it wouldn't go down forever. And maybe this part over here doesn't move at all, right? Or just rotates, right? Because it's the bolt is going to hold it in place, even though I didn't draw that there. So what direction of torque does that really mean? And so there's some ambiguity when we just look at how the system moves, but the mathematical definition for the direction of torque is that it's based on that direction of rotation by a right-handed rule. And in that sense, if you curl your fingers of your right hand in the direction that the system would rotate by this applied force, that is one way to get the direction that is implied by this torque, which in this case I think would be kind of into the board, into the screen maybe, depending on how you're looking at this. So maybe if you get out your right hand, you can try curling in the direction. Maybe curl your fingers, start out pointing maybe to your right and then curl them downward in the direction of this force. Because, again, you're kind of curling. Maybe I can draw this here. It's like if you curl your fingers sort of like for this direction of rotation, right? Because that's what is going to be achieved there. But then what happens is your thumb is pointing into the board. So I'll put a little X here to indicate like a vector pointing into the board. Another way to do this right-hand rule, though, is you take your fingers and you point them initially in the direction of R, and then you turn your fingers and make sure if, maybe you initially have, like, you might hold your hand out, maybe your thumb is pointing up. And then the second step is, okay, bend your fingers in the direction of the force F. Well, you're going to have to rotate your right hand to do that, or at least if you don't, there might be some weird crackling sounds as bones break and stuff. So don't do that. Do it the way your hand and your fingers bend naturally, right? So rotate your hand. That will put your thumb pointing kind of into the board, into the screen here. Now your fingers are able to rotate down in the direction of F. So that's kind of the two-step, maybe three-step, depending on how you look at it, 2 or 3-step, multi-step right-hand rule, as opposed to just the one-step curl your fingers right-hand rule. But in this particular case, they give the same answer. The torque implied by this situation here is into the board.